So our last topic in acid-base chemistry is polyprotic systems. Polyprotic as opposed to monoprotic. Monoprotic means an acid that has one proton to donate. So we've seen things like HA. All of your strong acids are monoprotic acids, except I can't write and talk at the same time. My timing is not good here. All of your strong acids are monoprotic except H2SO4. H2SO4 is a diprotic acid, also known as a polyprotic acid. So you can have something that's diprotic, 2 protons to donate, triprotic, 3 protons to donate, but lumping all of those things together, an example of triprotic is H3PO4, lumping all of those things together that have more than one H to donate, polyprotic. There are lots of examples of diprotic and polyprotics. I just walked through your strong acids back here. H3PO4 is not a strong acid. But I just walked through your strong acids here. But there are many, many, many more weak acids in the world than there are strong acids. And many of those weak acids are polyprotic. When you have a polyprotic acid, the proton is lost sequentially. What does that mean? Well, you go from your diprotic thing, you lose one H to become conjugate base, and then that conjugate base becomes the acid in the next step to become a dianion, double conjugate base thingy. It's not really how you say that, and you lose another H. They're lost sequentially. There's going to be different amounts of each of these species in solution. Like I said, sulfuric is one of the polyprotics. It's a strong acid, but it's only strong when it loses the first H, like losing the first H happens completely. Losing the second H in sulfuric, losing the second H does not happen completely. Most polyprotics are weak, like carbonic acid here. Carbonic acid loses one H to become bicarbonate. Bicarbonate loses another H to become carbonate. Oh, brain fart. Okay. The conjugate base in step 1 becomes the acid in step 2. Yeah, I actually said that. The first proton is lost more easily than the second. Yeah, okay. If we write a Ka expression for our first reaction, we're going to call it Ka1. That would be H plus times HCO3 minus over H2CO3. If we write a Ka expression for the second reaction, let's call it Ka2 because we're creative like that. H plus times CO3 2 minus over HCO3 minus. Okay, cool. The first proton is lost more easily than the second proton. What that actually means is Ka1 is always, always, always greater than Ka2, always, because the first proton is always lost more easily than the second. The actual numerical values for these Kas, times 10 to the negative 7 times 10 to the negative 11. That's a pretty significant difference. Table 15.5 from your textbook is here, and it has lots of diprotic and polyprotic acids. Sulfuric, I've already said, is one. It's got a very large Ka because it's considered strong for losing its first H, and then its second H is actually lost reasonably easily. But a lot of things like oxalic acid, less strong, sulfuric acid, carbonic acid, hydrosulfuric, phosphoric, that was our example of a triprotic. These are some examples that your textbook gives you the Kas of. But there are many, many, many di- and polyprotic acids in the world. Many, many, many. Okay, let's see what kind of math we can do with polyprotics. It is reasonable to assume that for weak polyprotic acids, if the Ka1 is much bigger, lots bigger, as in 1,000 times bigger, than Ka2, all of the H plus in solution comes from this first dissociation. This amount of H plus would be a very tiny number. The H plus produced from this second dissociation is a very tiny number. This one's small. This one's very tiny. So because it's very tiny, we can solve for H plus using rice, in the first reaction only. We get to kind of ignore that it's polyprotic, period, because we pretend like this is just a standard weak acid, Ka, to solve for our pH. Having a super tiny Ka2 means almost no conjugate base from the first step, almost no H plus in solution comes from this dissociation. So what that means is the concentration of H plus and HCO3 minus are the same. What? Hold on. If we wrote this over here where I can draw something underneath it, all I'm doing is copying that first equation, HCO3 minus. We would do a Rice table that would have some number here, minus X plus X plus X. So the concentration of H plus is equal to X, as is the concentration of HCO3 minus. That's because the Ka2 is very small. You're not going to change these concentrations very much whatsoever from the second dissociation. This reaction favors reactants so strongly that you have very little products in solution. So if we were to write a Rice table for our second dissociation, we would write this. But the thing is, there is some H plus at the beginning of this, and there is some HCO3 minus, but there's no carbonate. So at the end of this table, we would be a minus X and a plus X. So the concentration of H plus is whatever it was up here, plus X, and the concentration of bicarbonate would be whatever number it was up there, minus X. Well, if Ka2 is tiny, that means X is also tiny. So that means this number and this number remain about the same. Let me show you that in a typed up version. There's my Ka2 expression. And if I plug in the values from my Rice table, H plus X times carbonate, bicarbonate minus X, well, we said these are the same from the first Rice table. And after you subtract and add a tiny, tiny X value, it's still practically the same. So forget that. We actually get to cancel out both of those things. Again, because they are the same number from above, it's some number over the same number. We get to cancel it out completely. I feel like this is a very confusing explanation so far, but the take-home message is the concentration of the dianion in solution is equal to Ka2. Did we follow that? The concentration of the dianion in solution, says it back there, is equal to Ka2 because these values are the same because all of those H plus and HCO3 minuses come from the first acid dissociation. Ugh. Okay, I'm ready to draw some pictures. You ready to draw some pictures? Ooh, I love pictures. This is a weak diprotic acid being titrated by strong base. I know that because it starts low and ends high, and this is kind of slopey in the beginning, so it tells me it's weak. So if I'm going to draw pictures of all these little beakers along the way, beaker A. Beaker A is before I have added any strong base. Beaker A has H2A and only H2A in solution. All right. Beaker B. We have started to do that first net ionic equation. Let me write it down here so that I can write down a little bit more. Beaker 2, we've started to do that first net ionic equation, but we've not yet reached the equivalence point. At this beaker B, we've added some hydroxide, but we have run out from the hydroxide every time at the end of our limiting reactant table. We start with some amount of H2A. We still have some left over. We start with 0 of this, and we start gaining some. So at beaker B, we've got some H2A and some HA minus. I'm going to put one of each, and then we're going to figure out what kind of ratio I should really have. If my equivalence point is at 25 milliliters, halfway to the equivalence point, that's 12 divided by 2, That's a divided by, or multiplied by 1/2. That's 12.5 milliliters. And the magic halfway to equivalence point, that's where pH equals pKa. That's where H2A concentration is equal to HA minus. That's where my buffer equation would say pH equals pKa. So we are just over halfway. We are beyond the 12.5 milliliter mark. At 12.5 milliliters, you would put 2 of each of these in solution. But we're just beyond 12.5 milliliters, so I'm going to say we have more HA minus than we have H2A. That means in my picture, I'm going to put 3 of these and 1 of those. We see my logic, kind of, sort of? Okay. So if we go on to beaker C is at the first equivalence point. Well, that means the bottom row of my limiting reactant table has all of the H2A run out. And there will be 4 HA minuses in solution because we started with 4 H2As. D looks like it's between my 2 equivalence points, but it's not halfway between. That's a little bit off, my little line. It's not halfway between. It's prior to halfway between. So that's going to mean my second equation has started happening. Maybe I should change color so that we can follow along more easily. I don't know. My second equation has started to happen, but I'm prior to the point of HA minus equaling the concentration of A2 minus. So this means I've got HA minus 3 of those because I've got more HA minus than I have A2 minus. Follow me? E should be the same but different. Don't you love when I say things like that? It should be a mixture of H2A. Nope. It should be a mixture of HA minus and A2 minus, but the ratio is flip-flop, that you've got more A2 minus than you have HA minus because it's past halfway to the equivalence point. Beaker F is going to be real tiny down here. We'll make it real wide. F should have only A2 minus in it, 4 of them. And beaker G, we still have 4 A2 minuses because they don't start disappearing in solution. But we've started to accumulate excess strong base. So we're going to stick 1 little hydroxide in our picture. You have to get to the point where you start looking at a titration and saying, what do I have in solution? And you have to be able to look at a curve and know, what do I have in solution? You need to be able to look at limiting reactant tables, the start and the end, to say, what do I have in solution? You need to be able to, knowing what you have in solution, you need to be able to solve for a pH after that. Yeah? Yeah. Okay. This titration starts at high pH, ends at low pH, so it's a base being titrated by acid. It's harder to tell in these diprotics sometimes, but this one's already labeled, so it's a weak base being titrated by strong acid, and the reason I know that is because that little legend at the bottom tells me, as it does over here. So this is a molecular equation, but really we care about the net ionic equation / equations. The first net ionic equation that's happening in this reaction is CO3 2- is reacting with an H+ to create HCO3-. Then, at this point, we've got all HCO3- in solution. We start reacting that HCO3- with some more strong base to create H2CO3-. Strong acid. I think I said strong base. Ugh. We start reacting HCO3- with strong acid, more strong acid, to create H2CO3 at the end of our titration curve there. And then finally over here, if we were drawing a picture, we would show excess H+, excess strong acid in our solution down beyond my second equivalence point. Okay, that's actually not the point of this slide. I don't know why I waited till the last slide on this video to point out that when you have something polyprotic, the volume of acid or base needed to titrate the first proton is equivalent to the volume required to titrate the second. So it took you 25 milliliters to get to your first equivalence point. It takes an additional 25 to get to your second equivalence point. You ready to do things with polyprotics? I think so. Our last acid-base topic, we're going to miss it. Goodbye.